Welcome back. In this section, we'll be looking at solving trigonometric equations. That's any equation where we've got one or more trigonometric function in it. Now, we're going to have to be careful for any of these problems to look at the domain that we've been given, because depending on where we're looking for our solutions, we might find one solution or multiple solutions or even no solution. If you're thinking about the graph of tangent for just a minute, and if I asked you, where is tangent of x equal to 0, or in other words, where does it cross the x-axis, there are different answers that you might give depending on where I tell you to look. If I tell you, please look between negative pi over 2 and pi over 2, then there's only one place where tangent is 0, and that's when x is 0. But if I tell you instead to look over the interval from 0 to 2 pi, there's three places where tangent is 0, at 0 and at pi and also at 2 pi. Maybe there might be no solution if I say, please only look between pi over 4 and pi over 2. Tangent of x is never 0 there. If I ask you to look for the interval of all real numbers, well, tangent is equal to 0 in a bunch of places, infinitely many places. At 0, at pi, at 2 pi, and all the negative versions of those, and so on. So if that were the case, we would have to give our answer more generally as x is some multiple of pi. So x is equal to k times pi, where pi is an integer. So that is something that we're going to have to think about throughout. Where exactly am I looking for my solutions? Because we only want to find solutions in the interval we've been given. Now, we're going to start out with questions where there's only a single trig function in the equation. So not two different trig functions or multiples of the same trig function. Just a single trig function, maybe with some constants in there as well. So the first thing that we'll want to do is isolate the trig function that we have. So moving any constants to the other side, dividing by any constant multiples that we've got, so that we just have trig function equals to a number. And when you're at that point, you really should think about the range of your trig function, because it's possible that you might have arrived at something where there's no solution. So, for example, if you had simplified your equation and got to the point where sine of x is equal to 3, well, then you could stop and say there's no solution because 3 is not in the range of sine x. Once you've done this, once you've rearranged it, and once you're confident that there is some sort of a solution, then we can use our inverse trig function. So if you had your equation written as tangent of x equals to some number, and that number happens to be in the range, then we can go right ahead and rewrite this as an inverse to a trig equation. Tangent inverse of whatever the number is equals x. If you happen to have a secant, cosecant, or cotangent function, then you'll probably want to use your reciprocal identities first. So, for example, if you had secant of x equal to a number, I would first rewrite that as cosine of x is a reciprocal of that number, and then I'd be able to say, okay, cosine inverse of the reciprocal of that number equals x. And of course, I'm doing that because we've talked about inverse sine, inverse cosine, and inverse tangent. We haven't defined an inverse secant or an inverse cosecant or an inverse cotangent. So for those three functions, you're going to want to write those in terms of sines or cosines or tangent first. Now, once we've done that, we can then evaluate that inverse trig function. And once we've also done that, then we can use that answer to find all the values in the interval that we've been given, which will solve the original question, which will solve that original problem that we've been given. So isolate our trig function. If there is an answer there, then rewrite it as an inverse trig equation, find the value of that inverse trig function, and then use that to find all of your solutions. So we'll start with the most straightforward one. We've got a trig function already isolated. Sine x equals root 2 over 2, and we're solving in that interval from 0 to 2 pi. And we already have our trig function isolated, and I definitely do know that this is in the range of sine x. Sine x, the range is from -1 to 1, and that value is less than 1. So we are definitely in the range of sine x, so there will be a solution. And the solution can be found by first looking at sine inverse of root 2 over 2 and having that be equal to x. So we took our trig equation and we rewrote it as an inverse trig equation. And now all we need to do is evaluate what is sine inverse of root 2 over 2. And this is where you might use your special triangles. We know that the 90, 45, 45 triangle, the pi over 4, pi over 4, pi over 2 triangle, the value for sine of pi over 4 is root 2 over 2. So the solution that we get from our inverse trig function is pi over 4. Now again, that's only the solution that the inverse trig function gives you. That's not necessarily all the solutions that are in that interval. Because again, remember that sine inverse is only going to give us output that's between negative pi over 2 and positive pi over 2. And we're looking for any solutions between 0 and 2 pi, all within one full revolution. So we're going to need to remind ourselves that there's not just one place where sine would have a value of root 2 over 2. One of those places would be at pi over 4, that's for sure. However, remember that there is another quadrant where sine is also positive. So another solution would be found in quadrant 2. In quadrant 2, with that reference angle of pi over 4, in other words, for the angle 3 pi over 4, that also should have the same value for sine as pi over 4. So now I can say that what we actually have as our solutions are just two values. We have pi over 4 and we also have 3 pi over 4. So I'll just say that since sine of pi over 4 and sine of 3 pi over 4, they're both equal to each other and equal to root 2 over 2, then the solutions are pi over 4 and 3 pi over 4. And those are all the angles that are in that interval where sine of x is equal to root 2 over 2. Okay, let's do one that involves a little bit more work on our part. And so for this one, first I'm going to rewrite this as a single cosine function on one side. So I'll bring the 3 to the other, and then I'll divide by -4. And I have cosine of theta equal to 1/2. All right, so we know that if cosine of theta equals 1/2, that there is an angle theta that would satisfy that, because cosine, its output is between -1 and 1, and that value definitely is in that range. So good for us. We know that we're going to find some solutions here, and we're looking for all the solutions that are in that interval from 0 to 2 pi. So first I'll find the one value for theta by looking at cosine inverse of 1/2. And that will be one value for theta. And for this I'm going to use my special triangle, my 30, 60, 90 triangle. Pi over 6, pi over 3, pi over 2. And if we're looking at that 30, 60, 90 triangle, you can see that cosine of pi over 3 would be adjacent over hypotenuse. Cosine of pi over 3, that would be 1/2. So that means that one value for theta will be 1/2. That's the value we get from our inverse cosine function. We also need to remember that we're not just looking for one solution, we're looking for all the solutions in that interval. And there's two places where cosine has a value of 1/2. Remember that cosine is positive in quadrant 1, but it's also positive in quadrant 4. So if we look at the angle that's got the reference angle of pi over 3 in quadrant 4, and that would be the angle 5 pi over 3, that also has a value of a half for cosine. Cosine of pi over 3 and cosine of 5 pi over 3, they all have a value of a half. So our solutions here would be pi over 3 and 5 pi over 3. I do want to be kind of careful here. Remember that when we're saying we're solving in this interval, then the values that I'm looking for have to be between 0 and 2 pi. So if you were thinking about the angle that I just talked about, 5 pi over 3, and if you decided that you were thinking of it as negative pi over 3, even though, yes, those angles are equivalent to each other, they are coterminal, it's not the solution that we're looking for, because this would not be a value inside that interval. So unfortunately, you would be incorrect in that case if you said the other solution was negative pi over 3. Although negative pi over 3 and 5 pi over 3 look the same on the x and y axis, they both have the same terminal side, negative pi over 3 is not in our interval, so negative pi over 3 is not one of our solutions. So the only solutions then are pi over 3 and 5 pi over 3. All right, let's do some more. We've got a cotangent problem, so I'm going to start by rewriting this as a single trig function. So root 3 cotangent of x equals negative 1, or cotangent of x equals negative 1 over root 3. Or in other words, tangent of x is equal to negative root 3 over 1. And if you're looking at our special triangle for the 30, 60, 90, we can see that for pi over 3, tangent of pi over 3 would be opposite over adjacent. So we know that tangent of pi over 3 would be positive root 3. We're looking for tangent to be negative root 3. Or in other words, we're looking for x to be tangent inverse of negative root 3. Now, since we know that tangent of positive pi over 3 is positive root 3, then we know that tangent of negative pi over 3 is negative root 3. So we do have one possible value. However, that value, negative pi over 3, that's not in our interval. This is what I mean by saying that we might get values that come from our inverse trig function that actually do not solve the original equation. So if you're using your inverse tangent function and finding a value for x, you find the value of negative pi over 3, and that's because tangent inverse has as its output from negative pi over 2 to positive pi over 2. However, that value of negative pi over 3 is not inside my interval. So when I'm stating my solutions, negative pi over 3 will not be part of it. But that does tell us where we'll find our solutions. Remember that tangent has two places where it's going to be positive and two places where it's going to be negative. It's going to be negative in quadrant 4, and it's also going to be negative in quadrant 1. We know that the angle negative pi over 3 would give us the right value for tangent of negative root 3. But like I say, that value of negative pi over 3, that's not how we're going to think of that angle, because that angle is not in this interval. So instead, I'm going to think about it as, instead of negative pi over 3, I'll think about it as positive 5 pi over 3. Because, of course, that has the same reference angle of pi over 3. Similarly, the second solution that I'm going to find would have to be in quadrant 2, and would also have to have a reference angle of pi over 3, which means that the other angle that I'm looking for must be 2 pi over 3. So there are two solutions that we find here. The two solutions are we have 2 pi over 3. That's the solution that's in quadrant 2. And 5 pi over 3, that's the solution that's in quadrant 4. And we always should just double check and make sure that yes, these indeed are values that are from that interval, and I'm not including anybody who's not part of that interval. And in that interval from 0 to 2 pi, I know that there's exactly 2 places where tangent would be negative, and one would be in quadrant 2 and one would be in quadrant 4, and those would be those values there. Okay, so this one we won't be able to find the exact value for theta. And we know that not just because the question tells us that we're rounding our answer off, but if I'm just thinking about solving this, sine of theta is equal to negative 0.7, I'd be looking for theta to be sine inverse of negative 0.7. And I know that that's not something that I can find a value from a special triangle. So I'm going to need to use my calculator here. And the same sort of caution that I gave earlier, I'll give this again. Remember that the inverse trig function that we're using, sine inverse, that we want it to have its output in radians. So make sure that your calculator is in radians mode first. And so if I enter what is sine inverse negative 0.7, and I've got my calculator in radians mode, I find a value for theta that is approximately negative 0.775. And of course we need to remember that that is in terms of radians. So the angle that I found is negative 0.775 radians, but of course that's not a number that's inside this interval from 0 to 2 pi. So I'm going to need to think about what are my two solutions that I'm going to have. I know that there are two solutions because between 0 and 2 pi, there are two quadrants where sine happens to be negative. One is in quadrant 3 and the other is in quadrant 4. Now, for the angle that's in quadrant 3, we can think of that as having the same reference angle, which would be 0.775 radians, and we've gone past 180 degrees or past pi radians, so this could be thought of as pi plus 0.775. That would be the value of that angle in quadrant 3 in terms of radians. For the one that's in quadrant 4, again, I'm going to think about this angle, but think about it in terms of being a number between 0 and 2 pi. So rather than thinking about this angle as being negative 0.775, again, I'm going to think of the reference angle as being 0.775 radians. I know that one full circle would be 2 pi, and so I've gone 0.775 radians less than 2 pi. This angle I could think of as being 2 pi minus 0.775. And when I'm finding the exact or the approximate values for things, and I'm putting these through my calculator, the 2 pi in this case is the same pi that we're talking about when we were finding areas of circles. So my two solutions then that I find, one of them is 2 times pi minus 0.775, which is about 5.508. And the other solution that we find, which is at pi plus 0.775, which is at 3.917. So we find approximately two solutions, 5.508 approximately, and 3.917. And both of these, again, these are values that are in terms of radians. So this is not 5.5 degrees, it's 5.508 radians.